A federal report says your heat pump is losing efficiency for one avoidable reason, not the equipment. In September 2014, the National Institute of Standards and Technology published a 104-page technical note on residential heat pumps. Not the brand, not the compressor, the installation. You already know the checklist. Filter, bushes, thermostat. None of that explains the bill. 8 things explain why. The last one is a second federal document that an inspection program blames for most of what it finds wrong. Number 8. A technician starts a system on install day, it runs, and that gets treated as proof the job was done correctly. That assumption is where most of this list hides. Inside every outdoor unit sits a small heater wrapped around the compressor, called a crankcase heater. Its job is to keep the oil inside the compressor warm enough that refrigerant does not dissolve into it during cold weather. Cut power to that unit, whether from a breaker trip, a storm outage, or a technician who left the disconnect pulled overnight, and that heater goes cold with everything else. HVAC School's own field guide for technicians specifies 24 hours of continuous power before a cold unit gets restarted. Skip that wait, and the compressor risks slugging on startup with liquid refrigerant, a mechanical stress that shortens the life of the most expensive part in the system. That 24-hour rule lives in a trade manual almost no homeowner ever reads. For a step, nobody schedules a follow-up visit to confirm. After a storm outage, or a service call, where the disconnect gets pulled and the crew moves on to the next job, there is no meter that records whether the wait actually happened. The manufacturer's warranty language assumes the step was followed. Nothing in it accounts for the outage that came first. The compressor rarely fails that same week. It fails early, years later, on a bill that never mentions the outage. Nobody came back to check. The next one shows up on the coldest days of the year, and it looks far more alarming than it is. Number 7. Somewhere in the coldest weeks of the year, an outdoor unit starts putting off visible steam, and for a moment it looks like something is wrong. That cloud is the defrost cycle doing its job. Ice builds up naturally on the outdoor coil in freezing temperatures, and periodically the system reverses itself into cooling mode for 5 to 15 minutes to melt it off, which is why the unit briefly feels warm to the touch and throws steam into cold air. Lennox and Trane both document this as standard operation. Almost nobody reads a manufacturer's field literature before an outdoor unit starts steaming in January. What the manufacturers document less clearly is what a defrost cycle looks like once it stops behaving normally, a cycle repeating far more often than the 5 to 15 minutes Lennox and Trane list as standard, or a coil that never actually clears, points to a real fault, usually tied to the airflow or refrigerant problems further down this list. The panic response is what makes it worse. Cutting power mid-cycle to stop the steam interrupts a melt that was already most of the way finished, and traps the remaining ice inside the coil instead. The service call that follows treats a defrost cycle as the emergency, while the actual fault sits further down this list, still waiting to be found. Those first two explain what your system is doing in a given moment. They say nothing about why one heat pump leans on expensive backup heat every time the temperature drops, while another rarely calls for it at all. That difference comes down to a document, and we are not there yet. Number 6. That National Institute of Standards and Technology report from the opening of this video named 5 installation errors, with the largest measured impact on performance: duct leakage, an undercharged refrigerant line, an oversized heat pump, low indoor airflow, and an overcharged line. Every item on that list traces back to something a technician handled or overlooked on install day. The brand bolted to the wall does not appear anywhere on it. A 104-page federal technical note spent more of its pages on ductwork and airflow than on any single manufacturer, because that is where the study found the actual losses concentrated. 2 of those 5 show up as symptoms long before anyone calls them by name. A house where rooms far from the indoor unit run noticeably colder or warmer than rooms close to it is a house losing conditioned air along the duct run in between. The fault NIST ranks first. A system that reaches the thermostat setting and shuts off within minutes over and over all day is a system oversized for the house it was sold into, another item straight off that same list. The instinct once either symptom shows up is to call for a refrigerant top-off, but an overcharged line sits right next to an undercharged one on that same NIST ranking, doing similar damage in the opposite direction. Adding refrigerant to a system whose real problem is duct leakage does not fix the leak. It stacks a second installation error on top of the first, invisible to anyone reading a single combined number on a utility bill. The next item could be the most expensive line on that bill, and almost nobody itemizes it that way. Number 5. When a heat pump falls behind on a cold morning, most systems do not simply run the compressor harder. They switch on a second heater entirely, made of electric resistance coils sitting inside the air handler, usually called auxiliary heat or strip heat. According to Energy Vanguard and Trane's own technical literature, those electric strips cost roughly 2 to 5 times as much to run as the compressor doing the same job, a gap most homeowners never see itemized on a bill. A utility statement lists one combined number for heating, with no line separating what the compressor spent from what the strips did. The higher draw breaker sits in the panel under a label most people never learn to look for: auxiliary heat or strip heat or E-heat, pulling far more current than the compressor's own breaker for the same degree of warmth. And nothing on the bill ever flags which breaker did the work. A household running on strip heat for even a handful of cold mornings a month can be paying for a second heating system it never agreed to install. That heater earns its keep during a genuine cold snap, doing work the compressor physically cannot do alone. The problem is only when it fires on an ordinary, unremarkable morning, for reasons the next 3 items on this list explain. 4 of these are behind us, 4 are still ahead, and the one that ties the rest together has not come up yet. Green Exposed opens a document like this every week, the kind most homeowners never see cited anywhere else. If that is useful before your next service call, the subscribe button gets you the next one first. Number 4. A thermostat carries 2 different settings that get confused with each other constantly, and the mix-up is an expensive one. Auxiliary heat is automatic. It kicks in alongside the compressor when the compressor alone cannot keep up, and it switches back off once conditions allow, a small icon or a line of text the only sign it fired. Emergency heat is different by design. According to Trane and HVAC.com's own documentation on the distinction, it is a manual override that shuts the heat pump's compressor off completely and runs on the electric strips from item 5 alone, full-time, at full cost. The 2 settings look almost identical on a display, and the difference between them is whichever one got left in place after the last repair. A technician flips emergency heat on to keep a house warm, while a compressor is down for service, finishes the job, and moves to the next call. Nothing in the system prompts anyone to flip it back. The setting has no timer and no expiration. It stays exactly where the last technician left it, for however many winters follow. The homeowner living with that forgotten setting gets a heating bill that reads like a much colder winter than the one outside, on a system that never disclosed it had been running on strip heat alone, full-time, since the repair. The next item is a habit that feels like common sense, right up until it costs you real money every winter. Number 3. A homeowner who grew up in a house with a furnace learned to turn the thermostat down at night and back up in the morning to save money. On a heat pump, the Department of Energy's own guidance on operating and maintaining the system advises against that exact habit. A furnace can catch up from a big temperature drop, cheaply. A heat pump recovering from a large overnight setback often cannot close that gap on the compressor alone, so it leans on the auxiliary heat from item 5 to force the temperature back up faster. The overnight savings gets paid back, at 2 to 5 times the rate, by breakfast. The habit itself is not the failure point. Small, steady setbacks of a degree or 2 still save money and rarely trigger backup heat. It is the big overnight swing that trips it, the exact habit a furnace rewarded and a heat pump quietly punishes instead. Everything so far has been visible or audible: a breaker, a cloud of steam, a line on a bill. The 2 settings that actually govern that behavior leave no such trace, and nobody discloses whether they were ever configured the way the spec requires. That is where this gets uncomfortable, and it is also where the actual trick lives. Number 2. Every heat pump has what the industry calls a balance point, the outdoor temperature below which the compressor alone can no longer supply enough heat and the system needs backup to fill the gap. How low that number can sit depends on the house. A tightly sealed home holds the line lower than a drafty one. The Bonneville Power Administration's installation specification for heat pumps, last updated June 11, 2013, does not leave that number open-ended. A correctly sized system has to land at 30 degrees Fahrenheit or lower under its program. That number is supposed to come from a load calculation run on install day, matching the equipment to the house, before the first real cold snap ever tests it. Nothing requires a contractor to hand that calculation over, or to prove it was run at all. Most installation paperwork ends at the equipment model number and the warranty card. The only place the calculation resurfaces afterward is in how often the backup heat fires, a pattern a household feels in a bill, not a figure anyone reads off a form. A system sized to a balance point well above that 30-degree ceiling leans on expensive backup heat. Through weeks of ordinary winter weather, a correctly sized system would have handled on the compressor alone. Nobody hands a homeowner that comparison. It shows up as a bill that reads like a colder winter than the one outside, and nothing in the paperwork explains why. That gap between the number and the paperwork is exactly where the next item goes to work. Number 1. The Bonneville Power Administration, the federal power authority for the Pacific Northwest, runs a program called PTCS, and under it publishes a document with an unglamorous title, Lockouts and Balance Points Reference Guide. It has sections named exactly what they cover: importance of lockouts, aux heat, compressor lockout, balance point. The guide treats those two settings differently on purpose. Auxiliary lockout gets tuned to the house, and compressor lockout is built to need no tuning at all. Auxiliary heat lockout, the outdoor temperature above which backup heat is blocked from firing, carries a spec, 35 degrees Fahrenheit or lower. Compressor lockout should not carry a temperature at all. The guide says it should be disengaged, so the compressor keeps trying to heat the house at every outdoor temperature it is rated for. If a cutout is installed anyway, the PTCS installation specification, last updated June 11, 2013, caps it at 5 degrees. The guide states its own stakes directly. Incorrect lockout settings result in the majority of inspection failures. The single most common thing the program finds wrong, in its own words, on its own letterhead. A field study the Bonneville Power Administration published in December 2019 measured how often installs actually got this right, and the numbers read like an indictment. The aux lockout side first. Overall, 47% of homes checked had it locked out above 35 degrees, past the spec, in a region running its own oversight program. The single most common error was leaving the lockout disabled completely, handing control to whatever the manufacturer set at the factory, a default nobody at your install ever chose on purpose. Where a utility program actually reviewed the work, 75% of sites had that lockout set correctly. Where nothing reviewed it, that fell to 27%. Now the compressor side. At sites outside a program, 64% had the cutout engaged above 5 degrees, active exactly where the guide says it should not be active at all. None of that is disclosed at closing. There is no inspection that follows most residential installs to confirm either number was ever touched, and even if you go looking, both fields are often locked behind an installer code on a menu built for a technician's tablet, not for you. Whoever ends up on the wrong side of that pays whatever the factory default happens to cost, on a bill that never explains which of two settings decided how much of a winter ran on strip heat instead of the compressor. What that leaves you holding is two names and two values, already written into a federal reference guide: auxiliary lockout at 35 degrees or lower, tied to the balance point your own house sets, and compressor lockout disengaged, full stop, no negotiation. Nobody has to discover those on their own, because they are a public standard your installer was already supposed to meet, whether an inspection ever came to check or not. A system sold to you as equipment is actually run by settings, and most of them were never opened at your install. The 1914 report named what breaks, and Bonneville's guide covers the configuration meant to prevent it. Between them, you now know more about your own thermostat than the person who installed it ever told you.